Okay, so today I am going to discuss another problem from TIFR-PYQ 2021. Okay, so the problem states that here is the wave function. This is a simple kind of wave function and you have to find the average kinetic energy. So first please pause the video and give this problem a try by your own. Then if you don't get it, then look at the solution. Okay. So I will tell you some interesting things about this problem because this problem looks pretty simple, right? It's a simple diagram, nothing complicated, and you know what is how to find the average kinetic energy, right? The average kinetic energy is psi star minus h cut square by 2m d2 psi dx2. Okay, this kind of thing, and then integrate the with suitable limit. What is the limit? Maybe a to b. Okay, so this is the formula for average kinetic energy. You know that. But the thing is, if you see this diagram, the obvious thing that came to your mind that for this straight line d phi dx is constant, d2 phi dx2 is 0. This is already a constant, then d2 phi dx2 is 0. And again this is a straight line. For straight line d phi dx is a constant, but d2 phi dx2 again is 0. So overall, you should take this answer. Okay. Even at my time when I was in IPHD, I mean after BSc, I also, I mean when I was doing some PYQ, I also take that answer. But later I see this, and then I couldn't get that how they get this complicated answer. But the thing is, let me first tell you that how should you approach and why you should approach like this. Let me tell you later. Okay. The thing is that you know average kinetic energy is psi star, and let minus h cut square by 2m is there, so there is minus h cut square by 2m, and that is d2 phi dx2. Okay, and dx suitable limit a to b. Now you can simplify this. Let's take this h cut square by 2m outside. Okay, now do by parts. So this is your first function, this is your second function. So do by parts. So this is psi star. Oh, sorry. This is psi star, and if you integrate this, you will get d phi dx with suitable limit a to b. ठीक? Okay, so don't confuse with b in this question. There is also a and b. These are not this a and b. These are some other limits. So let me tell you, this is c and d. Suppose. Okay, so this is some other limits. This is not the a b that given in the question. Okay. Now what is your next step? Derivative this, differentiate this, and uh, keep this as it is. So it is d psi star dx into d psi dx suitable limit c to d dx. Now, if your wave function is well behaved, that means if in the lower limit this psi star goes to 0, and if in the upper limit also this psi star goes to 0, then this term is 0. Okay, so there is minus sign here, so make it plus. And what is this term? This term is simply mod d phi dx whole square, right? There is phi star, there is phi, and same thing. Okay, so this is mod d phi dx and whole square c to d. So this is a very important formula, and why this is very important, let me tell you. Let me give you a very common example. Most of you know this, the example of delta function potential. Okay, v is minus alpha delta x. All of you know that the wave function looks like this. So there is root under k e to the power minus kx for x greater than 0, and for x less than 0 it is root under k e to the power kx. So there is a discontinuity of d phi dx at x is equal to 0. So d phi dx is not continuous at x is equal to 0. So whenever you have to calculate that average kinetic energy, okay, so, or average p square, okay, so when we have do you have to do this d2 phi dx2, right? but there is a discontinuity in d phi dx. So d2 phi dx2 is not well defined at x is equal to 0. So the best technique to find the average kinetic energy or average p square for this kind of potential, that do the technique of mod d phi dx whole square. Okay, if you take mod d phi dx whole square, then calculate it in this is the even function, this is mod square, this is the even function. Okay, so calculate it in 0 to infinity limit and multiply by 2. 2 into 0 to infinity mod d phi dx whole square, and take your phi in this region. So at x is greater than 0, this is phi. Take d phi dx and do the integration 0 to infinity, multiply it by 2. Okay, so this is another good example where you need this kind of treatment. Okay, where your d2 phi dx2 is ill-defined at x is equal to 0. So why this is needed for this problem, let me tell you later. But first, do that problem. So write the diagram once again. Okay, so let me check. Minus a plus b to a plus b, minus a plus b to minus a, and a to a plus b, and this value is not given, so let us choose some, let's say c. Okay, so this the y value, the value of psi at this point is, let's we take c, but we have to determine c by the suitable normalization condition. Okay, so this is c, and let us now find the equation of phi in this any arbitrary point or at this point. This region is fine, this is a constant. Now this region, let's say it is x comma phi. This is a plus b comma 0, this point a plus b comma 0, and this point is a comma c, right? So let us determine the equation of motion, sorry, equation of straight line. So phi minus 0 divided by x minus a plus b is equal to c minus 0 divided by a minus a plus b. Okay, so that will give you psi is equal to minus c by b into x minus a plus b. So let us check that it is valid, that x is equal to a plus b, it is 0, so it is satisfying, and that x is equal to a, it is a minus a into minus b, so it is c. Yeah, it is satisfying. So this is the equation of psi in this region, psi 1, let's say psi 1. And for this region psi 2, you can find that by, I mean, you can automatically guess from this format that what should be your value of psi 2. Psi 2 will be c by b into x plus a plus b. Okay, so let us check this. At x is equal to minus a plus b, it is 0, so it is satisfying. And at x is equal to minus a, it is minus a plus a cancels, then plus b, yes, it is c. Okay, so it is again satisfying. So this will be the equation of psi 2. Yeah. Okay, and psi 3 for, this is psi 1, this is psi 2, and psi 3 is c. Psi 3 c. So let us now normalize it by suitable normalization condition. So integration of minus a plus b to a, uh, what is psi 2, right? This is psi 2. So psi 2 square dx plus, what is this, minus a to a, minus a to a psi 3 square dx. Okay, and your a to a plus b psi 1 squared dx. Yeah, so what is your psi 2? Psi 2 is c square by b square. Let me tell you one thing, that your normalization condition, this is a normalization condition, is mod psi squared dx. Okay, now you may thing that why I separate this. So this for different limits of x. So this for this region psi is psi 2, for this region psi is psi 3, and for this region psi is psi 1. So I separate it like this. Okay. So the normal formula is psi mod psi square dx. Okay. So and for different regions I separate like this. Let me erase this. So c square by b square x plus a plus b whole square. So x square plus 2 into a plus b into x plus a plus b whole square. And the limit is sorry, minus a plus b to minus a plus b to minus a plus c3 square minus a to a. So c square into dx, that is 2a. So it is simply 2a c square plus c square by b square x square c square by b square is a square minus 2 into a plus b into x plus a plus b n whole square, right? And a to a plus b is equal to 1. Okay, so c square by b, now x is cubed by 3. Okay, so minus a cube is minus a cube, minus a whole cube is equal to minus a cube plus a plus b whole cube divided by 3. Okay, now x squared by 2, so a plus b into a square minus a plus b whole square plus a plus b whole square into minus a plus b. Okay, so this is the thing. And now let's take this term also. So x is cubed by 3, so again it is a plus b whole cube minus a cube divided by 3. Okay, minus a plus b into x squared, so it is a plus b whole square minus a square, and it is plus a plus b whole square into a plus b minus a, that is b. This is the total thing, and there is plus let me write it here, plus 2ac square. Okay, so in this bracket this is total thing. Okay, so let make it plus, let make it minus, let make it plus, change the sign. Okay, so now there all the things are same, so 2c square by b. So there is all the terms are same. This term and this term are same. This term and this term are same. This term and this term are same. So let us take a 2 common. Okay. So this is a plus b whole cube minus a cube divided by 3 plus a plus b into a square minus a plus b whole square, a plus b into a square minus a plus b whole square plus a plus b whole square into b plus a plus b whole square into b plus 2c squared a is equal to 1. Okay, so let's do further simplification. This is a cube 3a squared b plus 3ab square plus b cube by 3. Okay, so let's erase that 3 because we already divided by 3. So square b plus ab square plus b cube by 3 plus a plus b into a square. So minus 2ab minus b square plus a plus b into b. Okay, so plus ab plus b square. Okay, so I am taking these two terms together, this term and this term together. plus 2c square a is equal to 1. 2c squared by b. Okay, so a square b plus ab square plus b cubed by 3 plus a plus b into minus ab. Okay, so plus b square minus b square cancel, so this is minus ab plus 2c square a is equal to 1. So 2c square b into a square b plus ab square plus b cubed by 3. Now minus ab into a minus a square b minus a square b minus ab into b is equal to minus ab square. Okay. Okay, so it simplified a lot. Plus 2c square a is equal to 1. Therefore 2c squared by b into uh, yeah, b cube by 3 plus 2c square a is equal to 1. I put 2c square into b squared by 3 plus a, sorry, 2c squared by b into, this should be a square, or let me check 1 minute. Psi 2 square, so 2c square into a, this should be c square by b square. I am doing a mistake, sorry for that. This will be c square by b square, because I recognize the dimensionally it will not match. There is a b square, there is a should, this should be, there is no b square. B by 3 is equal to 1. Therefore c square is equal to 3 by 2 into b plus 3a. So this is the main difficult thing of this problem, to find this normalization condition, because this is this and this means this cost a lot of time to find the normalization condition and keep track of your calculation. Okay, so this is a little bit difficult. I mean, the calculation difficulty, because it takes a lot of labor. So now this is done, and rest of the thing is very fine, because we already know the psi 1 and psi 2 and psi 3. So d psi 3 dx is simply 0. Don't bother about it. D psi 1 dx. What is d psi 1 dx? D psi 1 dx is minus c by b. And what is d psi 2 dx? D psi 2 dx is simply c by b. Okay. So now what is your average kinetic energy? H cut squared by 2m mod d phi dx whole square. Mod d phi dx whole square dx. Suitable limit minus a plus b to a plus b. So now let's separate this in different region. Sorry, h cut square by 2m. The first region defines 3d defy 2 dx, and for that this is minus c by b. But if you take mod square, it is simply c square by b square, and the limit is minus a minus plus a plus b. So minus minus give you a plus. For the second region, it is 0, and for the third region, it is again c square by b square into a plus b minus a. It is b. Okay, so h cut square by 2m into c square by b square. Now what is there left? There is a b left, and there is again a b left. Okay, so 2b. So it is h cut squared by 2 cancel m b c square. So now what is your c square? You already find, right? What is your c square? C square 3 by 2 into b plus 3a. 3 by 2 into b plus 3a. I hope this will be correct, but maybe not. There will be some calculation mistake can also be happen. Okay, it's match, I guess. H cut square by mb 3 by 2 into 3a plus b. I hope it's match. Uh, Yeah, it's match. 3h cut square. Let me write it more. 3h cut square by 2mb into b plus 3l. This is your average kinetic energy. So I already told you that what is the reason to take this kind of formula, because I already give you an example of the delta function potential. Delta function potential is ill-defined. The d25 dx2 is ill-defined at the point of discontinuity, that is x is equal to 0. So where there is a discontinuous jump in some point, then the wave function is ill-defined at that point. So you can't take this d25 dx2 treatment to find the average kinetic energy for this kind of delta function potential. Okay, and there is the also same thing happens here. There is this point, this particular point. Okay, what happened? I don't know what happened, but okay. These 2 points are ill-defined. These points are ill-defined. So that's why it's better to work with mod DeFi TX technique, this technique. So always remember this technique. Even for your variational principal problem, there is many kind of variational principal problems where you have to calculate the average kinetic energy. So it's better to take a single derivative rather than taking two derivatives, because two derivative is more complicated. If your wave function is e to the power ikx kind of thing, which is not suitable, not zero at plus minus infinity or suitable limit, then you cannot use this treatment, because this term should go to zero at your suitable limits. Okay, that's why we are neglecting this term. For this case, it is true, but for some cases it may not be true. But most of the cases it is true. Okay, so if this is true, then always use this statement, because here you have to take a single derivative rather than taking two derivatives. Okay, so yeah, this technique is very useful, and I probably know that who frames this question, because at the beginning of the semester I took a course Advanced Quantum Mechanics, okay, AQM. There is a Professor Rajdeep Singh Sharma, who actually discussing some problem of the complicated kind of potential tan hyperbolic x plus a by b minus tan hyperbolic x minus a divided by b, this kind of some complicated potential. And he shows that with suitable limits of a and b, this is a shy, sorry, this is shy. With suitable limits of a and b, your psi will convert to this kind of diagram, and then he asks to calculate the what is should be the average kinetic energy. The same kind of problem he asks in question in the beginning of the semester. Okay, so I probably know that this problem may be framed by Professor Rajdeep Singh Sharma. Funny thing. Okay, so that's it for today, and I think this is a very useful, very efficient technique to calculate the variational principal problems. Also, you always use this technique because you have to take a single derivative for this technique. Okay, so that's it for today, and next I will try to discuss some other years PYQ. The 2021 ends here. Okay, thank you.